Welcome to the Explainer. You know that feeling when a system starts to grow? Adding one seemingly simple feature means you have to go and change code in 10 different places. It feels like you're trapped in this impossible grid of combinations. Well, today we're going to build the solution to that exact problem. It's called the bridge pattern.
Okay, so here's our game plan. First, we'll dive into the messy problem that this pattern was born to solve. Then we'll actually build the bridge, piece by piece, and see its real power when we can assemble things at runtime. We're also going to clear up a super common point of confusion, bridge versus adapter, and then we'll wrap it all up with the key takeaway you need to remember.
So before we can really appreciate just how elegant this solution is, we need to feel the pain of the problem. It's this sneaky kind of complexity that just quietly takes over a codebase until it's a complete mess.
Let's start with a really simple scenario, something you've probably run into. Imagine you've got some kind of printer. You have two types, let's say a normal printer and a special packed printer. And they can each print to two different places, like the console or maybe a file. Simple enough, right? So how many different classes do you end up needing?
Yeah, the math here gets ugly, and it gets ugly fast. That simple 2x2 setup, that's 4 concrete classes you have to write and maintain. But what happens when you add just one more printer type and one more place to print? Suddenly, you're not at 6 classes, you're at 9. This is what we call the Cartesian product explosion, and it's a one-way ticket to a system that's impossible to manage.
And look, this isn't just some academic thought experiment. This has serious, real-world consequences. You get tons of code duplication everywhere. You're constantly having to open up and modify existing classes just to add a new feature, which completely shatters the open/closed principle. And of course, your test suite just explodes to cover every single combination. The whole thing becomes incredibly brittle.
And that brings us to the solution, which was defined perfectly by the Gang of Four in their famous design patterns book. What does this really mean? In simple terms, the whole goal is to separate what an object does from how it does it. When you do that, you can change either part without breaking everything else.
So how do we actually fix this mess? Let's build the bridge. We're going to see exactly how to replace that tangled web of inheritance with 2 clean, independent hierarchies. This is where we stop the explosion and start building something stable and flexible. You know, the core idea here is just beautiful in its simplicity. Instead of one giant messy inheritance tree, we create 2 completely separate ones. One for our abstractions, our printers, and another for our implementations, our output targets. And the connection between them? It's just a single, simple reference. The abstraction holds a reference to an implementation, and that reference, that's the bridge. This slide just nails the mathematical beauty of this solution. We fundamentally changed the equation of our complexity. We went from a multiplication problem, m times n, to a simple addition problem, m plus n. And that, right there, is the secret to managing complexity as your system gets bigger.
What you get from this is a really clean separation of concerns. The abstraction side, our printers, all it cares about is what's the message. So a normal printer might just pass it along, but a packed printer might add a special prefix. Meanwhile, the implementation side only cares about one thing. Where does this message go? To the console, to a file, maybe to a Kafka topic? And the most important part? Neither side knows anything about the specific details of the other.
Okay, now we get to the really cool part. The payoff here isn't just about having nicely organized code, it's about the incredible, mind-blowing flexibility you get when your application is actually up and running. Because those 2 hierarchies are totally separate, you can just mix and match them on the fly. You could have a factory that takes a string like packed and another one like Kafka, and it just builds the right packed printer with a Kafka writer right there at runtime. You don't need a precompiled class for that specific combination. It just works. Let's see the open/closed principle in action. A new business requirement comes in. We need to print to Google Cloud Storage. So, what has to change? You just add one new struct, a GCS writer. That's it. Your existing printers, your other writers, your factory code, it's all completely untouched. Your system is open for extension, but closed for modification. It's perfect. Now, this is a big one. It is super common to confuse the bridge pattern with another one called the adapter. But knowing the difference isn't just for acing interviews, though I'll tell you this is a classic senior-level interview question. It's absolutely crucial for making the right design choices. So let's make this distinction crystal clear. It really all boils down to your intent. The bridge pattern is proactive. You use it from the beginning because you see these 2 different dimensions in your system and you know they're going to need to change independently. The adapter pattern, on the other hand, is reactive. It's a patch. You already have two things that weren't designed to work together, and you need to build something to make them compatible. So let's just lay it all out. The purpose. An adapter makes incompatible things work together. A bridge decouples an abstraction from its implementation. Design time, you use an adapter after things already exist. You design with a bridge from the start. And the structure? An adapter wraps one thing to look like another. A bridge creates two parallel hierarchies. You've got to know this distinction cold.
All right, so after going through all of that, what's the bottom line? Let's distill everything we've talked about into the most important stuff you need to walk away with.
So, in the source code example for this pattern, the tests actually achieve 100% code coverage. And that sounds amazing, right? Perfect. But as any experienced engineer will tell you, that number can be really, really misleading. And here's a true principled engineer-level insight for you. 100% coverage is the floor, not the ceiling. It only tells you that your test suite ran every line of your code. It says absolutely nothing about whether that code did the right thing. Correctness is proven by your assertions, the part of your test that actually verifies the behavior of the system. So if you remember only one thing from this explainer, make it this. The bridge pattern is your #1 weapon against the combinatorial explosion. It keeps your system flexible, it keeps it maintainable, and it lets the what and the how evolve independently, which is a perfect example of the open/closed principle in practice.
And that is our deep dive on the bridge pattern. It's such a powerful tool for building systems that can scale in complexity without collapsing under their own weight. So now I'll leave you with this one question to think about. Where in your own code, in your own systems, is there a combinatorial explosion just waiting for a bridge to be built?